A few minutes later.
Run faster! There's a dinosaur! Don't stop! Keep running! Oh no! She got eaten! We have to run faster! Phew! I think we finally escaped. Wait, how fast were we actually running? Good question. Maybe this graph can tell us. Let's find out how to calculate speed.
Meanwhile.
Well, this isn't where I expected to end up.
Long story short, I was sprinting away, looked back for 1 second, and got swallowed by a dinosaur. I'm currently sitting right inside its stomach. It's surprisingly roomy, but I don't recommend it. While I was running for my life up there, nobody was tracking my data. The dino certainly wasn't. Okay, so how do we map up exactly what just happened? How do we turn a panic sprint followed by getting eaten into actual math? To do that, we need a visual diary. Welcome to part 1. What is distance time graph? Now, here is our grid, the foundation of the whole lesson. Let's look at how it works. First, look at the horizontal line at the bottom, the x-axis. This always represents time. Time moves forward and never stops, which is why it sits comfortably at the bottom. We measure this in seconds, minutes, or hours. Next, look at the vertical line on the side, the y-axis. This is our distance axis. Crucially, this tracks how far away something is from its exact starting point. We measure this in meters or kilometers. Finally, look right here where both lines meet in the corner. This is the origin. It represents our exact moment before everything began, where time was at 0 and the distance was always at 0. Now, let's take my T-Rex escape and turn it into data points. Watch how my journey literally draws the graph. Phase 1 was my sudden sprint. For the first 5 seconds, I ran flat out and covered exactly 30 meters. To plot this, we find 5 seconds on the bottom, move up to 30 meters on the side, and mark the spot. Then, we connect the start to this point. We get a straight line sloping upwards. This steady slope tells us I was moving at a constant speed. But then came phase 2, the chomp. I got swallowed and end up sitting right here in the T-Rex stomach. I've been stuck here for 5 seconds. Did time stop? No. Time kept ticking from the 5th to the 10th second. But did my distance from the start change? Not at all. I'm trapped in the same place, so my distance stays locked at the 30 meter. This creates a perfectly flat horizontal line. A flat line means zero movement, and it means I am completely at rest. Before we end part 1, there is a huge detail that we need to clear up. When people see a straight line sloping upwards, like our first segment, they often think, oh, it must be physical running up a steep hill. But that's a trap. A distance time graph is not a map of the physical ground. My actual case happened on completely flat ground before I got eaten. The line slopes upward purely because my distance away from the starting point was increasingly as time ticked forward. The slope represents a change in distance, not a physical hill.
Now, let's move to part 2, gradient and speed. Imagine 3 runners are competing in a race. We have runner A, runner B, and runner C. Take a few seconds and think about this question. Who is the fastest runner? Can you tell just by looking at them? Maybe not. But what if I told you that mathematics can help us identify the fastest runner without even watching the race? So, let's find out. To answer our question, we are going to find out what is speed. Speed is a measure of how fast an object is moving, and to work out the speed of an object, you need to know how far an object has traveled and how long it has taken the object to travel the distance. Before we can identify the fastest runner, we need to understand an important idea, gradient. So the formula for gradient is gradient equals to change in distance divided by change in time. Now look carefully at the speed formula. Speed equals to distance divided by time. Do you notice something? Both formulas involve distance and time. This means that on a distance-time graph, the gradient actually represents speed. The steeper the graph, the greater the speed. So, how do we find speed using a distance-time graph? Step 1. Choose 2 points on a line. Step 2. Find the change in distance. Step 3. Find the change in time. Step 4. Divide the distance by the time. This gives us the speed, or in other words, the gradient of the graph. So, let's apply this method to our runners. So, let's calculate the speed of each runner. So, for runner A, distance traveled divided by time will give us a speed of 20 meters per second. Runner B, distance traveled divided by time gives us a speed of 40 meters per second. And for runner C, the speed is 60 meters per second. So, now let's compare the results. The runner with the highest speed value will be the fastest runner. Therefore, runner C is the fastest. Now, it's your turn to try. Look at this graph carefully. We have 3 lines, X, Y, and Z. Without calculating, can you identify the fastest runner? I will give you 3 seconds. 3, 2, 1. The answer is runner X. Why? Because runner X have the steepest line. Remember, on a distance time graph, a steep gradient means a high speed. Before we finish, here is an easy way to remember today's lesson. Imagine climbing a mountain. A steep mountain will rise quickly, just like a runner moving at high speed, and a gentle hill rise slowly, like a runner moving at a lower speed. So remember, steeper gradient equals to higher speed, while gentler gradient equals to lower speed. And that is how we can use a distance time graph to identify the fastest runner. Now, let's try this question to see if you really understand gradient and speed. Ali and Siti are cycling to school. Ali travels 800 meters in 4 minutes, while Siti travels 800 meters in 8 minutes. On a distance time graph, whose line will be steeper? Explain your answer.
Now we will go to part 3, horizontal line and negative gradient in distance time graph. First, I will talk about horizontal line. Horizontal line means stationary in the distance time graph. For example, if you are waiting at the bus stop, your distance from home doesn't change, but the time keeps ticking. So the gradient is 0, and also meaning the speed is 0. Now let us visualize how is the movement using the graph. So at the right side, we can see the example of distance time graph. And at the left side, there's a boy from his home, which is the original position, 0 meter, and also the bus stop at 50 meter. First, we can see when the boy goes from 0 meter to 50 meter at the bus stop, the time goes from 0 minutes to 5 minutes. Hence, the graph moves upwards from 0 minutes to 5 minutes, and the distance changed from 0 to 50. However, from 5 to 10 minutes, the boy stopped at the bus stop and he didn't move. His distance does not change. Hence, the graph becomes horizontal from 5 to 10 minutes. The distance keeps the same, which is 50 meters. In conclusion, horizontal line in distance time graph means the time is moving forward. Hence, the line extends to the right. But the distance is not changing. Hence, the line does not go up or down. Next, I will talk about negative gradient. What is negative gradient? Negative gradient means that the line slopes downward from left to right. So, before we go into negative gradient, we will first look at positive gradient first. Look at the police car. When the police car moves from 0 meter to 100 meter, the graph moves upwards from left to right. You can see the balls move from 0 to 10 seconds and from 0 meter to 100 meter. Then, when we go to the negative gradient in the distance time graph, we can see the police car is moving backward from 100 meter back to its original position 0 meter. And you can see the graph is moving from 100 meter go downwards to 0 meter, but the time goes from 10 seconds to 20 seconds. So, to conclude, we can say that in a distance time graph, a negative gradient represents the object moving backward. The object is returning to its starting position, and we can say the object is moving in the opposite direction of what was defined as forward. Now, let's do a simple questions. A distance time graph shows a horizontal line from 0 to 5 minutes, followed by a line with a negative gradient from 5 to 10 minutes. So, what does this tell us about the object's movement? Choose from A, B, C, and D.
That's all for today. See you next time. Bye. Okay. Let's go to lunch. Let's go.
Okay.
Okay.